week and continue with the next weeks before we continue lab 3. So today I hope so that we can proceed lab 2 so we can save our time, not do the replacement lab. Okay, the lab 2 is about amplifier, BJT common emitter amplifier. But this session only focus on DC analysis, not AC analysis yet. We only focus on AC analysis. This chapter, I think, Madam Bayar already taught you how to do the DC analysis, and there's a lot of it's not very difficult to solve these questions. Only know how it flow, and we can do by referring the formula that we already learned. So today they have some section here that we need to accomplish. First, we have pre-lab calculations. We need to do pre-lab calculation. Means that we do a calculation before we proceed this lab. And we have DC operation, means that we do a measurement on the DC circuit, and we have a portion mark for discussion, 5%, 5 marks, and finally, of course, we have the conclusion. We need to know what you understand about these lab sessions. All right, total mark is 40%. All right. Okay. So what we will learn from this lab 2. So first objective is we will compare the amplifier theoretical and practical DC operation value. So we can identify, then we have realized that they have some different, the value that we compute or we make a calculations with the measurement on multisim. And then we will see on the particular the cushion operation point itu Q point. Then we will draw our load line and see whether our Q point. Then we make a comparison between the theoretical and measurement. And then from this lab, we will determine the transistor operations, and then we see what are different when the beta vary. And finally, we need to sketch the DC log line for the given circuit. All right. So for the introductions, this lab, the common emitter configuration will be investigated. So we will do the common emitter like we commonly learn in lecture. This common emitter amplifier typically uses a self-biasing scheme and has a relatively linear output. All right. The common emitter amplifier is characterized by a high voltage and current gain. So uh, the 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 motivations we do the amplifier is we want to amplify the input from the small signal become high signal, bigger signal. So how do we measure the scale of the scalings of our amplifier? So we will measure the AV, how many high voltage that we can produce, and we also can observe how much current we can produce from the amplifier. So later on we can see details. The amplifier typically has a relatively high input resistance, 1 until 10 k ohms, and is generally used to drive medium to high resistance load. The circuit for the common emitter can be seen in figure 1. Okay, this figure. It is used in application where a small voltage signal need to be amplified to a large voltage signal. Since the amplifier can drive low resistance load, it usually cascaded with a buffer that can act as a driver. Okay, so so usually in the this common emitter amplifier configurations, um, we always put our input Vs or voltage source on the base um, side, and we can produce our voltage output on the collector side. So to identify to determine the how much a scale up voltage that we can produce, so we need to find the gain. So find the gain, we need to uh, take out the V out, V output divide by voltage source. Then we can obtain the the gain of our transistor can produce, and also current. So we can take current output divide by current input. All right. So by referring to figure 1 here, if you realize we have two type of signal. One VCC is direct current type of source, and we have VS. Voltage signal is analog sources. So in the amplifier, we will superimpose between DC and AC. However, for this lab, we only focus on DC analysis. We can neglect of analog signal input along with the capacitor. So, okay, what the component involved? We have multimeter, transistor. Now we not use 1N914 that only for diode. Here we will use NPN. We have two type NPN and PNP. Today we will use NPN type of transistor silicon. So the body number is Q2N3904. And then along this transistor, we need to set up the common emitter circuit that we have R1, RB1, RB2, we have RE, we have to RE, R1, RE2. We also have RC, R load, and capacitor. Because of this lab only focus on the DC analysis, so they not provide us the voltage source. However, if we do the DC analysis, um, you must bear in your mind that we need open the coupling capacitor um, to us enable us to do the pre lab calculations. All right. So inside this statement, based on figure 2, calculate the DC current. We need to find DC current of IP, IC, IE, along with DC voltage, VB, VC, VCE, VE, and VLoad. By given beta number is 10, 100, and VBE is 0.7. Record the value in table 1 answer sheets. All right. I think this is table 1. So table 1, we have a pre-lab calculation that we need to do a calculation on our paper first. Later on, after do this calculation, we can proceed with the simulations inside the multisim. All right. before we proceed the procedure to implement with the multi-sim, we need to do the pre-calculations. So, so how do that? The first procedure that we have learned with the Madam Maya, she said that we need to open coupling the capacitor. So why we open circuit for the coupling capacitor? The reason is if you see the formula of the capacitor, resistance of capacitor, we can analyze him as Xc. Resistance of capacitor is equal to 1 over 2 pi f C. So in the DC, since in the DC, we have no frequency. So we can assume that frequency is 0 if 1 times, if anything time with 0, so we got 0. If 1 over 0, we got answer is 0. Means that if have any capacitor in a DC analysis, we need to open that circuit. So here we will open. Here will be open, so we will remove the R node. So here will be open. There no shortcut over here. Means that we have a series of resistance. So if we do a reconfiguration by removing the capacitor, we can make a simple and easy computational. All right. Mm, okay. Previously, we have the amplifier circuit like this, but now in the DC analysis, first we need to short circuit if we have a AC source. First, in the AC analysis, we need to short any of uh, AC voltage source, or we open circuit if AC current source, if any AC current source. Okay, and then we also open circuit, we short circuit if have inductor, or we need to open circuit if we have capacitor. So here we already short the AC source. So now we need to open circuit for the capacitor. So we need to open here, open, open. So we got the circuit like this. We have RC, we have BJT NPN, and R1, RE1, RE2. And then we have parallel of resistance RB1 and RB2. So it will circuit common on emitter. We have base, collector, and emitter here. So its source, our source effective, we 50 volt for the VCC. So to make an easy configuration or the common configuration, previously the easy way is like we only have VCC. In easy way, I draw it in the easy way. We have PNP BJT. We have only one RE, and we have one RB, and we have VBB. Then connect with ground. VCC, RC, RE, VBB. We have RB. These are uh, our common. So to make it a common configurations, so to make it RE, we need plus RE1 to RE2. So here RE equal to RE1 plus RE2. So how about VBB and RB? It's because here we have two resistant parallel. So to determine the RB, we need to parallel R2 and RB2 and RB1. So first of all, RB2 times with RB1 divide RB2 plus RB1. So now we will get the RB. So how do we find the VBB? VBB at these locations. So to find the VBB, we need to the voltage divider. Voltage divider formula is voltage dissipation between RB1 and RB2 where the source is 15. So RB2 over RB1 plus RB2 times 15. So we got VBB. So we got VBB. All right. So when since our question asks us to find the IB, IB, IC, and IE, so we need implement current Kirchhoff law uh, to 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 determine the value of IB. So the formula is by using current Kirchhoff law. The voltage supply equal to voltage load. So voltage load here is IB RB plus we have here VBE. So plus VBE. So plus with IE RE because it has the value not common. So we need to uh, take the value of IE RE. So how to leave only one RB. So relation between RB and RE like this. So just assume that IC is nearly equal to IE. So as we know, IC equal to beta IB. So if we replace IC with the IE, we can replace the equation inside our main question, the main equation. So VBB equal to IB RB plus BBE plus beta IB times RE. So by leaving one side with the IB, so IB RB plus beta IB RE equal to VBB minus VBE, then IB equal to VBB minus VBE over RB plus beta RE. Alright, VBB we got from here, when the RB we got from here, VBE equal to 0.7. So VBE have, RB also have, beta based on the lab model said beta equal to 100 and RE equal to RE1 plus RE2. So based on that, we can find IB. So solve one calculation, we got the IB. By replace value, we got the IB. So now we finish for base emitter current flow. So now this is base with current flow. Now we have another flow is collector to emitter flow. As we know, by using the current Kirchhoff law, we see VCC equal to IC RC plus, here we have VCE plus IE RE. Okay, as we know, we already has a IB. So IC formula equal to beta IB. So we have already IB, just calculate from here. By using this formula, we got IB. So IB times beta equal to 100. 100. So we got IC. Alright. And then formula to get the IE equal to alpha IC. Wait for a while. IE over IC. Betul. So the alpha equal to beta equal over beta plus 1. Beta we already have, so we can get the alpha. So by replacing alpha here, we got the value of IE. So since IC we got, and we can get the IE later. Okay, finish for the first task. So we already found the way to find the IB, IC, and IE. Now we need to find VB, VC, VCE, VE. Okay. How do we find VB? VB at here. So VB equal to IB RB. So IB already found, RB already have, so we got the VB. Okay. Then we need to find VC. VC equal to IC RC. Later we need to find VE, IE, RE. Then if you want to find VCE equal to VC minus VE. So all data we can find by using this flow. So until now, have any question want to ask me? If you have confusing or any questions want to ask, please, I'm open to the floor if you have a questions. So how about we load? Uh,
Sir,
yeah,
saya ada soalan.
dia Brian.
Kenapa IC is almost equals to IE ya?
Oh, dia sebabkan dia almost, dia bukan equal dah, dia almost. Untuk dapatkan VBB ni kita pakai assume that IC most equal to IE. Kalau you tengok nilai alpha pun, kalau you kira lah IE over IC, it almost 0.98 or 0.99. So they almost to 1. If 1 times IE, we will get IE because IC equal to beta IE. Terbalik. IE equal to beta alpha IC. So the value is mostly equal. Kalau kita tak pakai yang kita ambil assume IE equal IC, kita susah nak solve dalam base emitter punya circulations. Yang ni you boleh
Oh,
refer dalam chapter Madam Baya punya lecture note.
okay,
Hmm.
thank you.
Kalau you tak buat assumption macam ni, dia susah untuk you buat further calculation. hmm. Nanti kalau Brian boleh refer balik dekat nota Madam Baya. Dia memang selalu dia akan assume IC uh, equal more, lebih kurang lah, itu equal to IE. Sebab dia alpha tu
Oh,
memang mostly alpha tu dia nearly to 1. Bila darab dengan lebih kurang 1 tu dia akan dapat value yang sama lah.
okay, thank you.
Okay, welcome. Alright guys, boleh try compute. Boleh try compute for the first this table. You boleh carilah value dekat untuk pre-lab calculation. Cuma dekat vload, kalau kita tengok dekat vload tu dia dekat sini. So when in the DC analysis, kita dah open circuit CC2 ni, kita open circuit coupling capacitor ni. So means that once kita open dia tak ada lah vload ni. So bila tak ada unload, dia tak adalah vload. So mostly vload we assume as 0. So you can prove your calculations with your measurement later. Untuk sekarang ni saya bagi masa you guys untuk carilah value sekian ni, value pre-calculation first. don't worry, we not try to finish this lab by this week, because I think there's a lot need to do. We will continue next week.